Welcome to Mathlink Academy, where we connect the dots. I am Mr. C, and in this unit, we're going to talk about how to sketch the graph by analyzing the functions of the graph. So we want to analyze the graph and then have a nice sketch of it. So let's get started. So the first thing we want to talk about is analyzing the graph of a function. Our overall goal right now is really want to sketch it, but I want to bring some components that we need to know in order to sketch the graph. So there is a certain order how you want to do this and think it through to get the sketch of it. So some things you want to know and to get within your function is the X and Y intercepts. So that's not too bad. Setting X equals 0, solving for Y, or setting the equation equal to 0, solving for X. Does give us the X and Y intercepts. The domain and range is good to know. The continuity, if it's continuous, vertical asymptotes, if you can differentiate, find the relative extremums, those max and min points. Find the concavity. Also find the point of inflection. At times you may have to find the horizontal asymptotes. And then infinite limits at infinity. These are basic things you want to analyze before you take the graph or make the sketch of the graph. For instance, let's look at this graph that we have. F of x is equal to x cubed minus 25 plus 74x minus 20. Now, if you graph this on your calculator, and you always can graph this, but sometimes it's good to sketch the graph before you graph to get an idea of how it looks. If you have a small window, you may end up with something like this and say, oh, it just have a maximum point at whatever the maximum point is. But if you enlarge your window, you may see something different as far as the complete sketching of the graph. And that's the key. This side, the right side, is actually more of a complete picture. And if you don't do the analyzing the graph of a function, you may actually graph an incomplete part of the graph. And so sometimes graphing on a calculator may not give you the whole picture depending upon the viewing of the window, okay? So let me show you this. You may, when you analyze the graph of a function algebraically, you'll end up with something like this and then realize that that point, that our circle in purple, is actually part of the graph because you didn't enlarge your window. And so we're going to try to avoid graphing just a small part, but graph the whole graph like I did before. Now, a few things with this graph I want to show you. You have, in this case, you can look here, a maximum point. I'm going to do a different color green so you won't confuse the red. Here's a max, there's a local max and a local min. So one of the first things we may want to do is find the first derivative to find the max and the min. Then it looks like we have some point of inflection, maybe one here, maybe there's one somewhere else. But then you want to do the second derivative to find the point of inflection and the concavity, if it's concave up or concave down. Now to review the concavity, the increasing, decreasing, and also the max and min and point of inflection, look at my other videos that talks about that, because if you look at those videos, it will put it together with this video of analyzing the graph of a function. So let's look at this example and quickly sketch the graph of this function. So the first thing I'm going to do is find the first derivative. That will at least gives me some extremums, max or min points, possible max and min points. So this I'm going to do 4x cubed minus 12x squared. And then let me, on the side here, I'm gonna write this in blue, factor this out. I want to factor out a 4 and an x squared, which leaves in the inside x minus 3. Making sure we did that correctly. Always gotta double check myself here. So in this case, we have x equals 0 as a critical point, and also x equals a positive 3 if I did that correct. And it looks like in this case, when we do this, we have these values here. And I'm going to stop here for a second. Now I'm going to do the second derivative. So let's put that in black here for the second derivative. And this also tells me about concavity and possible points of inflection. So the second derivative here would be 12x squared minus 24x. In this case, I'm going to factor out, put this in green, factor out a 12x, if I did that correct, leaves an x minus 2. So we got x equals 0 and x equals a positive 2, our possible points of inflection. Okay, sticking with the second derivative, let's find the concavity. So let's do that in blue here. Stick with the second derivative. Let's find the concavity. So we have 0 and 2, and we're going to plug numbers into the second derivative. So notice we have f double prime. Numbers less than 0. So number less than 0 will be like a negative 100. So hopefully it's coming out on the screen. So here we go. So in blue that I underline, so I know there's a little hiccup on our video. These are critical points from the first derivative, and these are possible points of inflection from the second derivative that I did in green. And now I'm using the second derivative to find the concavity. So I'm going to plug in values in the first, second, and third region. So pick a value that is less than 0, like a negative 100. I'm going to plug it into the second derivative to find the concavity. Again, negative 100. I'm going to use the green over here, this green, to see that would give me a negative number, negative. A negative times a negative is a positive. So the answers here will be positive. Give me a number between 0 and 2. 0 and 2. We can use the value 1, plug that into the second derivative again, plugging it right here. That'd be 12, a negative. So a positive times a negative number is a negative. And then we're going to use a number greater than 2. I'll say 100. 100 times 12 is a positive number, one of that. So we got positive times a positive is a positive value. So this is going to be concave up, concave down, concave up. And notice that 2 and 0 are points of inflection. So I'm going to put that down. These are points of inflection. 2 and 0 are points are of inflection. So 2 and 0 are point of inflections. And I'm going to actually cross out this 0. X equals 0 is not a max or min. It's a point of inflection, going back to the green piece. Now we got to figure out what are the actual values at 0 and 2 in the original equation. So to find what those point of inflection was, you got to give me the X and the Y value. So we're going to find F of 0. Look back at the original equation. I'm just going to tell you, here's the original equation. That's going to give me 0. And then let's find F of 2 into the original equation. Here's the original equation. We plug that 2 into the original equation. We're going to end up, if I'm not mistaken, maybe a -16. So double check that. And so our points of inflection is 0, 0, and 2, -16. Now, I'm going to use the second derivative test on the value 3 to see if it's a max or min. I could have done the increasing and decreasing that we talked about in other videos, but I want to use a second derivative test. Hey, Mr. C, what do you mean by that? Well, I'm going to plug the number 3, this critical value that I got from the first derivative, inside the second derivative, the value 3. So I'm going to do this in blue. So when I plug it in, it will tell me if it's a max or min. It won't give me the y value, but I'm plugging 3 into the second derivative. Again, here's the second derivative right here or right here. Okay. And I don't care about the value because I just want to see if it's a max or min, and then apply the second derivative test to it. So 3, if 3 is in there, 12 times 3 is 36. That's a positive number. So we end with a positive. This will be a number greater than 0, which means it's a minimum. Again, we got to know what the second derivative test tells us. So in this case, 3 is a minimum, and to find what the y value for 3 is, we plug 3 into the original equation to get the y value. So since 3 is a minimum, I'm going to keep it in orange. It can be 3, and then we plug this 3 in to the original equation to get the y value. Okay. So 3 goes into that equation, and I think it gives us like a -27. You can double check me on the math. And there's our points. Now go ahead and write that down if you want to pause the screen, because we're going to go to another whiteboard and we're going to plot these points and get a sketch of this graph. Okay. So what we have here so far, we have found, and I did it on a different whiteboard so you can see this. We have found the minimum is 3, -27. We found points of inflections, 0, 0, 2, -16. We found concave up, and this is -infinity to 0. So write that clearer than I did. And then this is 2 to infinity. We found concave down is from 0 to 2. 0, 2 is the point. Or from 0 to 2, excuse me, it's not the point, but from 0 to 2. Now, for other things that we said we want to look at is maybe where X and Y intercepts. So let's look at the X-Intercept. So I'm going to do this in green, and then I'm going to erase it. So to find the X-Intercept, you set the original equation, which is up here, put in green, set it equal to 0. So x to the 4th minus 4x cubed. And then we'll factor it out. So this is x cubed. We're left with an x minus 4. And that gives me x equals 0 and also x equal to, in our case, a positive 4. So it crosses the x-axis at 0, 0, and also at, in this case, 4, 0. So let's write that down. And this is also a y-intercept. So our x-intercept is going to be x is 4, y is 0. Now to find the y-intercept is when you set x equal to 0 and solve for y. So looking at the original equation, if we plug in 0 for x, it'd be 0 minus 0, 0, 0, 0. So in this case, 0, 0 is also the x and y intercept, but I'm not going to write that down because it's also a point of inflection. So we're okay there. I think we're good so far for what we need. We don't have any asymptotes, no vertical horizontal asymptotes, and I believe we're good to actually try to sketch the graph of this function. So what we're going to do, let's look at what we got. Let's create our X and Y axis. So it's got a lot of low numbers. So this is 1, 2, 3, 4, 5. Here's 4. 1, 2, 3, 4. Here's a -4. And we can go by twos here. 2, 4, 6, 8, 10. And then down here by twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, down there. Now let's plot points and use what we have so far for what we analyze to get the sketch of the graph. So we said a minimum is 3, -27. So let's do the graph in green. So here's 3 over here, go down 27. It's about right here. We also have inflection points at 0, 0, green point here, and 2, -16, 12, 14, 16. So it's about right here. Again, this is a sketch. So that takes care of our minimum and our points of inflection. Now let's look at our concavity to see how this works. And then also, let me do this. I'm going to get the X-Intercept. Let's not forget about that. So that's 4, 0. So when I'm going to sketch the graph, I'm going to do it in blue. So I got all my points done in green. Now let's sketch the graph. So it concave up, or concave up is from -infinity to 0. Let's look at that, -infinity to 0. Concave up is -infinity to 0. Then it concave down from 0 to 2. So excuse my, then it concaves back up from 2, and it continues to go all the way up, and it cuts through that 4 right here. So this is how we look. So this is concave down. This is concave upwards, but it continues to go upward all the way to infinity, but it crosses that x-axis at 4. So it's going to continue to go up. And this is the sketch of the graph as we analyze certain components of the graph. Hopefully that makes sense, and how I arrange what to do first. Let's look at another function and sketch the graph of this by analyzing certain components of the graph. First thing we're going to do is take the first derivative of this function. So this is a new function. It gives us a -15 x to the 4th plus 15 x squared. From there, I can get our critical values, what helps us to find our max and min, our possible max and min, I should say. So I'm going to factor out a -15 x squared. So put it in factor form, make it a lot easier. This would be x squared minus 1. And so what we have here is x equal to 0 and x equal to plus or minus 1 are relative extremos. These are possible max and min. Now, our second derivative will find concavity and also possible points of inflection. So in this case, what we do here, we have this as a -60x cubed plus 30x. And then let me factor that out. I'm going to write this one in green. So you see this is coming from the second derivative. So as we factor out, we're going to factor out a 30x gives us a -2x squared plus 1. Okay, let's make sure everything looks good. I want to make sure we didn't make any mistakes here. Now let's continue with what we have to make sure. Set the second derivative equal to 0. That's in green. Therefore, we have x is going to equal to 0. And to solve this piece, we have to move the 1 over, be -1, and then divide it by -2, which is 1/2. So we end up with, I'm going to write this down as x squared is equal to 1/2. Now to solve for x is going to equal to 1 over the square root of 2, or the square root of 2 over 2 is another way of saying it. So I know I'm going kind of quick, but I'm giving you the values what they are. So we got x equals 0, and then also, and write this in green, x equals plus or minus the square root 2 over 2. And all those are possible inflection points. So let me underline what we have: our possible inflection points and our critical values that give us our possible extremums. Now, the next step I'm going to do is stay with the second derivative and find the concavity. So let's draw our number line. And again, it's the green values: 0, square root 2 over 2 positive, and a negative square root 2 over 2 negative. And we're going to pick numbers in between that: 1, 2, 3, 4 regions. So we have 4 regions: 1, 2, 3, 4. I'm going to start in the inner one, because in here I could pick a -1/2, and in here I could pick 1/2. And again, I'm plugging it into the second derivative and figuring that out. So I'm going to do that and get it out the way for you. If I plug in, I'm going to put it in red so you see it. And again, we're plugging these values in the second derivative. And so in this case, if I plug in a -1/2 in the second derivative, my answers will be negative. If I plug in a +1/2, which comes from here in the second derivative, gives me positive. If I pick a number greater than the square root of 2 over 2, like a +100, that would give me, in the second derivative, that would give me a negative value. And if I plug in a -100, coming from this first region, this first interval piece, into the second derivative, that would give me a positive value. So let's write down what we have so far, and I'll put this in blue. We have concave up being from -infinity to negative square root of 2 over 2. That's our positive. And we have another one from 0 in the square root of 2 over 2. And then we have concave down from negative square root of 2 over 2 to 0. And then from square root of 2 over 2 to infinity. Those are those red negative values. That's concave down. Now what we're going to do next is we're going to go to our next whiteboard and then write down all the summations that we have as far as how we analyze or what we analyze for this particular problem. Maybe do a few more things and then graph it. Now, before I go to my next whiteboard, even though we're about to go to it, I want to determine these points of inflections and the Y values, and also maybe possibly the Y values of our critical values. So notice this, guys. So with the positive, looking at the second derivative, those positive values, that means it's concave up, concave down, concave up, concave down. So we have 3 inflection points. So this top one that says x equals 0 as a max and min is not a max and min. X equals 0 is actually an inflection point. So all I have to worry about is 1 being a max and min point. And we can use the second derivative test for that. So let's actually figure out these values. Now, let's plug in. Let's start with our values here. Let's start with right here. X equals to plus and minus 1. And let's plug that into the original equation just to get the point. So when x is 1, we're going to plug 1 into the original equation. It's going to give us 1, -3 plus 5 is, our case is 2. And when we plug in a -1, it's going to give us a -2. So let's remember that. Let's also plug in 0 into this equation again, and that will give me 0, 0. And we know that's a point of inflection. Okay. Now I went to the whiteboard and I wrote everything that we basically have. Here's our original function. What's in blue is a possible max and min. And what's in green, we got from a second derivative, which is a points of inflection and concave up and down. Okay. So let's just see if we could work with what we have here. Again, you want to find X and Y intercepts, but we know it's going to cross the X axis or the origin at 0, 0. And so in this case, we're going to work with what we got so far. And it doesn't seem like we have any asymptotes. So we don't have to worry about horizontal and vertical asymptotes in this problem. So let's see how we can sketch this graph by analyzing what we have so far. Again, I'm going to plot the points. I'm going to use red to plot the points. We have 0, 0, that's a point of inflection. We have 1, 2, which is here. We have -1, -2, which is here. So it looks like -1, -2 is a min. This is a max. That's what it looks like. We also got other points of inflection. So I'm going to do something a little different. So I want to make sure I zoom in on here, guys. I'm going to erase this graph for a second and then make it a little bit bigger since our numbers are not so big. So let's zoom in, make it a little bit bigger. So I'm zooming in and I'm going to do this. I have this as the value 1. Here's a value of -1. And we'll go here, 1, 2, 3. So here's 2, 1, -2. Again, let's use points 0, 0, 1, 2, maybe 1, 2. We got concavity. So let's do blue with our concavity. We'll come back to this other point of inflection. That'll help us out. So we have concave up from -infinity to -√2/2. So that's about here. And the -√2/2 will give us this. So we have something like this, a concave up. And notice that is concave up. But then it goes concave down, and this should be -√2/2 to 0. Then it goes back to concave up from that √2/2, then goes back down here. The only thing we didn't do is find those X-intercept, which is no problem. You could have found the X-intercepts by setting the equation equal to 0, and it tell you where it crosses the X-axis. We have 3 places, one in the negative area, 0, 0, and then one in the positive. So that's the sketch of the graph that we have for -3x⁵ plus 15x squared. So that's the sketch of the graph, looking at some of the things that we analyze to get. So hopefully this helped how to sketch the graph by getting some different components and analyzing the components of the graph. Now, if you need more understanding, feel free to look back over this video and also look at some of our supplementary material that's on our Mathlink website. In that supplementary material, you'll also see other types of graphs that has asymptotes that you can learn how to graph that along with your graphs and other components that we didn't necessarily talk about in this video. Again, let Mathlink bring it together.